Okay, so this is super quick version of what we learned last year, but bearing angles deal with the direction that we are traveling, and we use the compass points. So we have north and south and east and west. Never ever smoke weed. And north, we're going to call north 0 degrees, and clearly between north and east there's 90 degrees, and we get 90 degrees bigger to get to south, which makes 180, and we get 90 degrees bigger to get to west, so that would be 270, and we get 90 degrees bigger, which is going to get 360. So you're saying, well, north has two numbers that go with it. Yes. So if I'm looking at north from the west side, north seems to be 360. If I'm looking at north from the east side, then north looks like it's 0. So if I am traveling at some distance over here where this is 10 degrees, if I know this is 10 degrees, then that's 10 degrees different than 90. Well, since I'm on the high side of it, I'm towards 0, so this must be 10 smaller than 90, so this is pointing at 80. So if I'm over here and this is 10 degrees, then I'm 10 on the big side of 90, so this would be pointing at 100. So if I'm 10 over here, that's pointing at 190. So that's the whole concept of bearing.
Okay, cool.
So you're just putting it in a number like this, and it tells you where you're pointing.
Cool.
But that only works in a horizontal plane. It doesn't work well when you're going up. So that's the concept of bearing. Super duper short and sweet. It's not a terribly hard concept. But that's the orienting that we do in here. So they had number 10 they were bothered by in part B. So let's do B10. In 10 we have a jet that's flying 42.7 meters per second south. So the jet's going this way.
We're recording this one?
We are totally reporting this. Now we're getting pushed 10.8 meters per second by a west wind. West winds push
West.
from the west. We always name winds where they come from.
Okay.
If we get a north wind, it's coming from the north, so it's shoving us south. So a west wind would actually be shoving us east. So that's going to be 10.8 meters per second. So that's what's really happening. So if my plane is pointing straight south, it ends up actually traveling over here. Now, the problem is, I asked 3 questions. One was, how long will it take to travel the distance south? I said the distance south is 95.6 kilometers. So you say, well, do I use this speed, or the actual speed that it's traveling? And, well, since the direction is south, we use the speed that matches the direction. So, and again, there's no mention of an acceleration here, so we're just going to use v equals d over t. We're solving for t. T is going to equal d over v. Of course, we have a problem here because this is kilometers and that's meters per second. So we're going to change that to meters, and then we're going to divide that by meters per second, so the meters cancel, and that gives me 2,200 seconds. Is that right?
Yes.
Tells you who actually did this,
Well, actually, yeah.
or you just glanced at the answer?
No, it's because like
We worked it out, but like,
it's because you didn't specify whether it had to be in seconds or minutes.
Okay.
So the answers you gave us were in minutes. So I just converted it to
yeah,
The answers were in minutes.
37.3 minutes.
Okay, so yes, you could divide that by 60 and get it in minutes, but that doesn't really help us do this any better. Now the second question was, if it took me this long, how far off course did I go? Well, the whole time I was traveling south, the whole time I was flying 2,200 seconds worth of flying, the wind was shoving me this way. So we're going to do the same thing, but this time we're going to see how far off did it go, so the t needs to come up. So we're going to say that 2,200 seconds, the wind was blowing 10.8 meters per second, which means I traveled 24 kilometers, basically, 24,000 meters if we're running the 260. So that was 24 kilometers we got shoved to the east. And then the third question was, well, where should I have been pointing? So I ended up over here. I wanted to go straight south. So where did my plane should have pointed?
Oh, you can get the angle and use it on the other side.
Yeah, I should have pointed this way so the wind's moving on the course and stuck me here. So in reality, of course, the airplane isn't going to fly this way, hover in midair, and wait for the wind to shove it over. So what happens is the plane is actually in this orientation the whole time, but it actually just goes through the air looking like that, which isn't helpful for the people watching. But oh well. And it is like that. It's kind of funky. You can see things, airplanes, especially if it's a windy day and you're near the airport, you can see the airplanes come in sometimes at funny angles like that because they have to. I had a friend who was big into model planes and the ones that you can fly, and you have to come in at an angle sometimes like that. It was really kind of cool. Yeah, and it's like that in you're in a boat that has a current that's going sideways too, where you have the wheel that's turning the propeller, and you actually have the wheel turned way over here. It's not like a car where you have to straighten it out. You keep the wheel turned, and it feels weird to not straighten the wheel out because you're so used to cars. But yeah, you just keep the wheel turned that way so that it keeps you going straight. It feels weird. Anyway, so if we're doing this, of course, we're looking for this angle, and this angle means, you know, these numbers all still work. So this is still 10.8 over here. So when we're looking for the angle, then we want to use negative tangent. And tangent, of course, is opposite over adjacent, so the opposite side is going to give us the 10.8, and the adjacent side is this 42.7. And when we do that, we get what? 14? So that gives me 14 degrees, but again, that's not my bearing angle. That tells me I'm 14 degrees away from this one. This one, of course, was pointing at 180. Since I'm on this side of it, am I getting bigger or smaller? Bigger, so that should be 194 degrees is where the, sorry, I should have drawn it here. 194 degrees is where this is pointing. Super duper simple, right? And then we have B11, which is the one some of you hyperventilated over. And your whistle. So we have a ramp, and we have a ball, and the ramp is 27 degrees, and we're going to pretend that there's no rotational inertia. But this is 5.27 rooms, and we want to know how fast the ball is going when it's zooming down here at the bottom. So we're assuming that the initial must be 0, and this of course is our and we're looking for how fast it's going at the bottom, so the VF is what I'm looking for, and we also want to find the time. So when we look at this, we say, well, VIVFD, that shows up in two different equations. The one that we want to do is that one. The other one that has VI and VF and D in it also has T in it, but it's easier to find A than it is to find T in this particular situation. So we're going to look at this. Since VI is 0, this part goes away. To find VF, I need to do that. So I'm going to have 2 is 2. I don't know what A is, but I do know my D is 5.27. So now all I got to do is figure out the A. So then I say, well, what's actually pulling me down? Well, if I have no friction, here I'm rolling, so rolling friction is so small, we're just going to ignore it. So the A is just G sine theta. So if it was sliding and there's sliding friction involved, that's different, but we're, yeah.
Can you explain why it's
Why is
G
it
sine
sine?
Yeah.
Yeah.
Why sine?
weight is pulling this way, because weight can only pull straight down. But the part of the weight that's shoving that way is the part that's doing the accelerating. And so we also have this part that would be providing the normal force. If I bring this down here, this makes a nice 90-degree angle. So this we call the parallel portion of the weight, right? And so because it's parallel to that, but this angle is the same as the angle of incline here. So this is the opposite side, and weight is the hypotenuse. Opposite hypotenuse is sine. So that's why it works, but it always works. So you're on an angle, you just know the angle of incline. It's always going to be g sine theta is your acceleration, assuming there's no friction. If there's more friction, then we add in other stuff, but this one didn't have this rolling friction. So here we're just going to have g sine theta, so actually you could shove that whole thing into here if you wanted to and do it all in one step. And you'd be in good shape. So you can try that. Square root of 2 times 9.81 times the sine of 3.7 I got 6.85. No. That would, I said you should get.
Yeah, I got that.
Hey, I like it when I get the right answer. Okay, the second question was, how long is it going to take to roll down the ramp? So again, we had the VI and we had the VF and we have the D, and this time we want to find T. So the best equation for that is, yes, if we have the D equals VF plus VI times T over 2, that has everything. So then solve for T, T just stays there, this comes up. The VF is going to go to the bottom. Since the VI was 0, we can ignore it. And we end up with that. So we had the D was 5.27. And the VF now we know is 6.5. Rain. That wasn't that bad, right? So easy.